This is Geometry, Unit 8, Day 11. We're working on inscribed polygons. In each diagram below, triangle ABC is a right triangle. Right triangles can be inscribed in circles because right angles is inscribed in the circle. Now, when we look at this, notice that we have a diameter. And that means that on one side is a semicircle, which is of 180 degrees. This angle is inscribed. That means that the vertex is on the side of the circle and that the sides of the angle touch the endpoints of this diameter. When it does touch the endpoints of the diameter, it's going to be half of the 180. So that's how we know we have a right angle. Notice that each of these triangles here are all the same way. We have a diameter, we have an inscribed angle. The inscribed angle happens to be touching the endpoints of the diameter. So since this is a semicircle, half the circle, since this is a diameter, we're going to take half of 180 to figure out what this inscribed angle is. That happens in all three pictures. The measurement of angle CAB is 90 because it's half of the 180. The measurement of angle ACB, that's this angle over here, we know the acute angles of a right triangle are complementary. So 90 minus 50 equals 40. The arc CAB. Notice that three letters need to be used for us to name a semicircle. If it's 180, it needs to have three letters, and if it's more than 180, it needs to have three letters. The measure of arc AB. Since this only has two letters, we can assume that the arc measurement is going to be less than 180. Well, let's look up here. Arc AB is right here. We know that the angle that opens up to touch it is 40. It's called an inscribed angle. The angle equals half of the arc. So that opposite arc is going to be twice as much as the inscribed angle. So it's going to be 80 degrees. In question B, the measurement of angle CAB, that's right here. We know the acute angles of a right triangle are complementary, so we can subtract to figure out what its measurement's going to be, and that's 26. We have 26 degrees for the third angle of our right triangle. The measurement of angle ACB down here, it's half of the semicircle, so it's going to be 90. The measurement of AB, arc AB. Well, we just mentioned that this should have been written with three letters. Because if it's a semicircle, the correct notation is to have it with three letters. So ACB, either way you think about it, we would consider that to be 180 degrees. The measure of arc CB, now notice how that only has two letters. That implies we're going to go the quickest way around, not the longest way around. That's how we know it's less than 180, because it has two letters. Well, we're going to take our 26 and times that by 2, because that's an inscribed angle. The angle comes up and touches the arc at CB, so the arc is twice the angle, or the angle is half the arc. Comes out to be 52 degrees. Here we're looking at a right triangle inscribed. This one's a little intimidating because it has some fractions. These are called expressions, variable expressions, because they have the x that goes with them. We want to solve for x. What do we know about the relationship between angle A and angle B? You've practiced this through the other two, and that's that angle A and B are complementary. They add up to 90 degrees. So there'll be a couple different ways that we could solve this problem. We could work with getting common denominators and working with the numerators, moving over the 5 and probably cross multiplying or something like that. But I would suggest to see what number does the 2 and 3 both go into. That's the number 6. So multiply each of these terms by a 6. 2 is your denominator. 2 goes into 6 3 times. So 3 times 1 gives you 3x. 3 goes into 6 twice. So 2 times 1 gives you 2x. There's no denominator here, so it's just 5 times 6, which is 30. And no denominator, so 540. Now notice we got rid of our fractions. No denominators involved with this. So we have 5x plus our 30, that equals 540. Subtract the 30. So we have 5x equals 510. Divide by the 5. And x is going to come out. 5 goes into 5 once. 5 goes into 10 2 times. So it's 102. Now we're looking at the measure of angle. Notice it's not an arc, but it's an angle. The measure of angle ACB. That is down here. It's an inscribed angle that's touching the endpoints of a diameter. So that opens up to an arc of a semicircle. So you know it's going to be half of the 180. Next, we're talking about a right triangle is inscribed in a circle. Well, to draw a right triangle inside of a circle, we need to know where the center is located. You can draw a diameter. It doesn't matter which angle you make that diameter. So we have this diameter going through, obviously, the center. Then to make our right triangle, the other two legs of our right triangle can be anywhere, as long as they're touching at the sides of the triangle. So now we have 180 on one side, and that's going to make 90 over here. The radius of the circle is 5.6. So here, from the center point to the side is 5.6. Well, if the radius over here is 5.6, we know it's 5.6 the other direction also, and that happens to be the whole diameter. And the diameter is the hypotenuse. So what is the length of the hypotenuse? The hypotenuse is 2 times 5.6, which is 11.2 centimeters. Alright, so next we're looking at the idea of quadrilaterals being inscribed in a circle. First, I want to talk about what can be true about triangles and being inscribed in a circle. I'm going to try something on my phone. I've drawn a triangle, and with this triangle, this is true about every triangle. Every triangle can be inscribed in a circle. It doesn't matter what size or shape our triangle is in. What happens is if we find the perpendicular bisector of a side, notice that all the perpendicular bisectors are going to touch at the same exact location. It doesn't matter what shape we have, the perpendicular bisectors are always intersecting at the same exact, their intersections are always at the same spot. So that spot happens to be one second. The center is at the intersection of the perpendicular bisectors, and we want to open that up and have a radius out to the side. Notice that circle perfectly touches and inscribes that triangle. So now we can move that triangle around, and notice that regardless of the size of triangle we make an obtuse triangle, and that intersection is on the outside. Make about a right triangle, and that intersection is right on the hypotenuse. Make an acute triangle, and the intersection of those perpendicular bisectors is on the inside. So regardless of your triangle, you can always inscribe it inside of a circle. But with a quadrilateral, that's not always true. A quadrilateral isn't always able to have all three or all four vertices touching the sides of the circle. So a quadrilateral can be inscribed in a circle if and only if the opposite angles are supplementary. So what we notice about D and F, they have to add up to be 180. The measure of angle D plus the measure of angle F have to equal 180. The measurement of angle E plus the measurement of angle G, they're opposites. They have to add up to equal 180. Of course, together, all of them are going to add up to 360. The sum of the interior angles of every quadrilateral adds up to 360. If the opposite ones are supplementary, then you know it can be inscribed into a circle. If one set of opposite angles are supplementary, then the other set will be supplementary to. So if you know two angles happen to add up to 180, the other two have to automatically add up to 180 because their total sum is 360. So now we're going to look at a variety of different examples. Here we look at example A, and we're trying to determine if this quadrilateral can fit inside of a circle, can be inscribed, it's called, in a circle. What do you see? What do you know about the numbers that would help you determine? What's the requirement for a quadrilateral to be able to be inscribed? The opposite angles have to be supplementary. In our case, we have 130 plus 70. That adds up to 200. So these are not supplementary angles. Therefore, you can use three dots to represent the phrase therefore. Therefore, this can't be inscribed in a circle. Because the opposite angles don't add up to 180, it can't be inscribed in a circle. In this case, we have a pair of opposite angles that are both 90. So 90 and 90 make 180. regardless of what these measurements are. We don't know what their measurements are, but together we know their sum has to be 180 also, because 180 here leaves 180 left to get to 360 total. So yes, opposite angles are supplementary, so therefore it can be inscribed in a circle. Letter C, we see that we have a pair of parallel sides. Well, remember that there are these angles called consecutive interior. And if lines are parallel, then what do we know about consecutive interior angles? They are supplementary. So now, what shape would this be called? We know that it has one set of parallel sides, has a pair of congruent, what we call legs. It's a trapezoid, so it's an isosceles. An isosceles trapezoid. What do we know that's special about an isosceles trapezoid? Base angles are congruent. So we know these base angles along the parallel line, they have to be congruent, and so do they across the top. So opposite angles are going to be supplementary. And since opposite angles are supplementary, we know that this isosceles trapezoid can be inscribed in a circle. Okay, so now we're going to solve for variable x's. What should be a plan for us? How are we going to set this up? You've got to be able to look at these pictures and come up with a plan for how you're going to go after a problem like this. Remember that opposite angles are supposed to be supplementary. So y plus 62 has to add up to be 180. So we're going to subtract the 62. So y is going to add up to be 118. Well, it happens to be the same thing going the other way. We have x plus 62 has to add up to be 180. Since this quadrilateral is touching the sides of the circle, that makes it an inscribed quadrilateral. And opposite angles have to be supplementary. So when we subtract the 62 across, we get 118. This one's a little trickier. What do you see? What would be your plan? Would you say that x plus y adds up to 180? That's true. They do add up to 180, but that doesn't help you reach their conclusion. There's an infinite number of options. Notice, if we take this arc, this is one of the ways we could do it. We take the arc from R all the way over to T, it would be called RST, and that's going to be 170 plus 40, which is 210. Well, we have angle X, which opens up. It's an inscribed angle, and it touches our circle at the R and the T. So it's half of that angle. So we're going to take our 210 and get 105. So we know that x equals 105. Now what do we know about the y value? X and y, we said, added up to 180. So 105 plus the y have to add up to 180. So subtract the 105, and y is going to be 75. Here we have another example. What do you notice? What information do they give us? Well, we know that opposite angles are supposed to be supplementary. So that means the 3x minus the 8 and the 5x plus the 2 have to add up to equal 180. Collect your like terms, which is 8x, and your like terms, which is negative 6. Add your 6 across. Divide by 8. Now here's a trick on how you can divide this out. 8 goes into 16 2 times. That would leave us 2 more to get up to 18. 8 goes into 26 3 times, which is 24, which is 2 left over, 2/8. Well, 2/8 is the same as 1/4. 1/4 could be written as 0.25. So you don't have to have a calculator, though I'm sure that would help you out. Okay, letter D. Look at this one. Come up with a plan on how you could solve for one of our variables, x, y, or z. One option would be pretty straightforward, to use the property of a quadrilateral, and that's at opposite angles, an inscribed quadrilateral. The opposite angles have to be supplementary. So we know that 2y plus 3y plus 5 have to add up to be 180. We get 5y plus 5, add up to 180. Subtract that 5 across, and then divide by the 5. 5 goes into 17 3 times, with 2 left over. Goes into 25 5 times. So y has to be 35. What would be our next thought? Looks pretty challenging to come up with z. But look at what x does. X comes over, its angle comes over and touches here, comes up and touches here. Well, this arc is double whatever that angle is. So if we say 108 plus 75, we're going to come up with 183. So 183 is that large arc. Well, angle x is an inscribed angle that touches the endpoints of that arc. So we know that the angle equals half of the arc. So the measure of angle x equals half of 183. So x is going to be half of that. So 2 goes into 18 9 times. Goes into 3 once. Alright? With 1 left over. So 1/2, you could call that 0.5, or you could call that the fraction of a half. 91.5. Now how does that help us figure out z? What do we know about z? could do that a couple different ways. You could talk about 360 minus the 183, but we also have opposite angles have to be supplementary. So we know that x plus z have to be supplementary. X is 91.5 and the z add up to 180. So z is going to add up to be 88.5. So there's a lot to that problem. You have to take each one individually. You may find this to be a little bit easier. What's your plan? What do you see? We know that opposite angles are supposed to be supplementary. So 4y minus 1 and the 65 are supposed to add up to 180. We can collect our like terms. 4y plus 64 have to add up to 180. Subtract the 64 across. That comes out to 116. Divide by 4. 4 goes into 11 just 2 times with 3 left over. 4 goes into 36 9 times. So we know that that's 29. A calculator is not required, but it would definitely make life easier. Here we have opposite angles. This quadrilateral is inscribed in the circle. So 3x plus 63 equals 180. They're supplementary. We'll subtract across the 63 to get 117. Divide by the 3. 3 goes into 11 2 times, which is 9, with 2 left over to get to 11. 3 goes into 27 9 times. So that makes x to be 29 and y to be, whoops, not. 3 goes into 11 3 times, which is 9, with 2 left over, 39. Y is 29, x is 39. Last question. Here we have a star below. All of the inscribed angles are congruent. Find the measure of the inscribed angle. Well, if this is an inscribed angle, it comes down and touches this arc right there. All of those arcs, if all the angles are the same, all the arcs have to be the same. Well, it's 360 all the way around it, and there are 5 arcs, so that comes out to be 72. So each arc is considered 72 degrees. It's their measure. Now, to figure out the inscribed angle, remember the angle is half of the intercepted arc. So 72 divided by 2 gives you 36. Now they asked us, what is the measure of all 3 of those angles? Actually, all 5 of those angles. We have 36 5 different times, and that's going to come out to be 180 degrees. Because if all the way around is 360, and these angles are accounting for 100% of it, and they're all half of that sum, so they have to be half of 360 again, which is 180. Hope you enjoy circles.